Okay, so now we'll have a recording from here on. Okay, I hope you have some fun with this. I'm trying to make some of these things fun because I think they're fun. I mean, a lot of good, a lot of enjoyment I get from doing various kinds of communications things, as well as circuit things and designs and just understanding how the world works, physics things. So let's see. All right, just some general points on the exam, on the whole thing. First of all, since other than Shadadi, I think you're all technician. You're all at least technician class licensees. So you've already gone through one set of questions. It's in the order of 300 to 400 questions. They're multiple choice answers, and the test consists of the test consists of for the general class will consist of 35 questions from that pool, and the extra will consist of 50 questions. You can miss 9 on the general, and you need 37 correct to pass the extra. It's about 70%. So it's typical of an exam. There is the exam information. I'm going to go over that with you too, but the exams are not it's a typical multiple choice exam. So the A, B, C, Ds are not in the same order on the exam that they are in a question pool. So don't remember A, B, C, D. That's not going to work. You have to understand. You have to know what the right answer is, not whether it's A, B, C, or D.
Of course.
Well, you never know. I am going to give you a reference called hamstudy.org, which has all the stuff, and we're going to talk about that in a second. Some good news on fees. When you got your technician license, you had to pay $35 for the 10-year period. Upgrades are free. So there is no $35 charge for these upgrades to general and extra. You will have to pay somebody $15 to take the exam at some official place. We at the Newport County Radio Club will hold a special exam session just for you guys in Portsmouth, probably at St. Barnabas Church in Portsmouth. But there are plenty of opportunities to take the test anywhere in the world. So if you're not local to us, then we'll try to hook you up with a local radio club, and then you can take the exam then and there. There are now opportunities to take online exams, but you have to be well monitored for that. So you need cameras, 2-angle cameras and so forth. It's quite, I don't say it's complex, but I think it's to me, we tried to do this, and it's quite a burden on the volunteer examiners who do this for free to try to organize the monitoring online. There are people who practice it and are good at it, and they will do it for you. So you can avail yourself of that. But the conventional solution is simply to take the exam on an iPad or a tablet. And you will take the exam with us exactly as if you were on the Ham Study website and doing a test. They can give you example tests to take, and you can you will take, when you do the actual exam, you'll get a test exactly like that. So you should be pretty familiar with the process by the time this is over. We're going to meet for 6 weeks. Virtually like this. There is one case where I have a commitment on the weekend. I'm doing a presentation at a microwave talk, and that is April 14th. So we're going to skip April 14th and have one the following week. So you'll have a week off, and you'll be able to practice your little hearts out on that. But it'll be 6 sessions, and I'm trying to move the current test date was the following Saturday, like it was Friday night, and then the test was going to be Saturday. I'm trying to move that out a week so that you guys got a week in between to.
That'd be nice. That'd be nice.
I don't know. I don't know how we're going to do it, but I don't want to force you to listen to the last class and then take the test the next day. There's plenty of time left in June to do it. So I'm negotiating that. I didn't get an answer on that today. We are having a class tomorrow, so anybody who fails will probably show up at this test next week. at this next week. But
They have an exam tomorrow, so if
some
they fail,
people,
they'll
yeah.
class.
And by the way, it's perfectly okay to study all the questions, memorize the answers, take the test, and pass. This is done all the time. I don't have a problem with that. What I'm trying to do in this seminar is give you an insight into what a lot of the technical material is in a friendly way, as well as where to go get information on all the other things. I'm trying to give you the reference material, not the answers to the questions. If you want the answers to the questions, that's going to be pretty easy to obtain because it's all over the web. Okay, so we do 6 sessions. There's no fee. People ask me about a book. By the way, I wrote an email with most of this information on it to you. If you have a book, I think you'll find it useful. A lot of people do like the book. I'm just not requiring it, any particular book, because all the information is online. Let's go to ham study. Is anybody not familiar with ham study? Does anybody want any information about ham study? Has everybody tried it, looked at it?
Yes.
Okay, so I don't have to spend a lot of time on how to use ham study. Okay, all of the questions are there. Make sure all of the questions are there. You can read all the questions. You can take tests anytime you want. You can take sections at a time. It'll ask you, there's a training mode. You can play flashcards with it. There's a lot of modes in ham study, but it's all the same pool of questions. I will try to tag all of my comments against those question numbers. So in the general, all of the sections are called G1, G0, G1, G2, G3. And then there's some have sections like G1A and G2B. So in all my slides, when I'm dealing with a topic, I'm trying to give you the reference questions associated with it, but I'm not doing it in order. That's the point I'm trying to make. You can email me anytime, k1ybe@yahoo. You can text me. I don't have any text limits, but I prefer the emails because then most every question I get, somebody else has. And so I can sometimes reply to your question by replying to everybody. Not necessarily identifying you as asked the question, but just so don't feel like you're asking a question and everybody's going to say, why did they ask that? That is the wrong way to approach it. But if you ask me a question, I would like to try to share at least my answer to the question because it might be useful to other people. It saves me some time. And everybody that does the test charges $15. It's sort of a regulated thing. And some people just put up the thing. Nobody's under 18, but if you know anybody who is under 18 that wants to get into amateur radio, the ARRL, the American Radio Relay League, will in fact offset the cost of the $35 for anyone 18 or under. So if you know somebody who wants to get into the hobby, they can do that part of it for free. Okay, all right. Here's my 2 main pieces of information. All of the material for all of the exam questions with explanations. And if you had a book, this is the place I would. If you don't have a book, this is the place I would go. AD7F0 has a wonderful website, and one of the reasons that I'm let me put this window. I've got several things on my screen that you're not seeing. Are you seeing everybody on the screen? In addition, do you see me moving this around? No. Yes?
See,
No.
Okay, good. All right. So let's see. What am I sharing here? I'm sharing my screen now. Well, let me do this. Give me a second. Okay, here's, I don't need that. Come on, all right. Here's 87F0 site. Can you see that though? You see that?
Yeah,
Yeah, okay. All right. He's got tons and tons of stuff here. One of the ones I like that's a lot of fun is this one. You might be a ham if, and so you could be a ham if you look at the full moon and wonder how much antenna gain you would need to get there. You might be, when a friend gets a ride from you and remarks that you have a lot of CBs in your vehicle, it turns into a half-long hour rant about how ham radio is not CB radio. If somebody asks you directions, you question whether to tell them about short or long path. And,
not quite sure what that is.
and there are lots and lots in here. There are some other ones like your cell phone ringtone is a Morse code message. You accidentally end your conversations on telephones with your amateur radio call sign. And you notice more antennas than road signs when driving on a road. And so these are some of the things you might be if you're a ham. And there's lots and lots of them, but that's a fun one if you want to have some fun while you're looking at the 8007 site. Let me back out of that for a second. What did I do now? I didn't want to go through all of these for you, but I thought you'd get a kick out of some of them. One other thing I wanted to.
I don't know what I mean.
Okay, I had my own that I guess I missed a slide. I don't think it's in it. If you can find your way on a map by adding and multiplying, you finished exercise 1. That means you're beyond technician class. If you understand useful RF signals, you will understand that useful RF signals have multiple frequencies in them. That's a general piece of information that you may not know. One frequency, no information can be sent. Let's see. This is what I hope to get you to get out of the class. I want you to understand how to look up materials that relate to the license questions and where they came from. I want you to try to understand alternating current circuits, which I don't think are much harder than plain old simple DC circuits if you follow a couple of the arithmetic rules I'm going on vectors. And I want to apply all of that knowledge to filters and components and especially safety in doing the hobby. So those are some of my goals, and I hope you enjoy them. I want to go back here and go back to 87F0 for a second, only for a second, because I just want you to know how much. So you go here, you can copy and paste this. I'm doing some of this stuff on my computer because I think some of you, like you open a new session, paste in 80F0s, and so he's got a general syllabus. He's got the rules. He's got references, lots of explanations, and along with the questions. So if you thought you needed a manual if you thought you needed a book, you probably don't. There's lots and lots of stuff in here. Let me see. Let me give you an idea, quick idea.
He said I should not have it.
Okay, so he does background, and you'll see a lot of my stuff has this as well. So he tends to be immediately looking technical to this stuff, and I try to avoid that, but I can't completely. So anyway, that's what's at that site. Okay, So that's a good reference if you get tired of listening to me. The seminar material, all of my presentations are at this link. You should have shared access to this link. If you just go to Dropbox, as I learned this evening, you will be asked to pay for some storage. There's nothing at Dropbox that you need to do for this course that needs you to sign up for anything or pay for anything. Dropbox this is a shared folder where all of the files that I use, the presentations are there by weeks, but the PowerPoint's even there, and there's a general syllabus for the whole thing. You can see how I'm breaking it up if you're interested. So there you go. That's any questions on the exam, how to take it, and so forth? Not the questions, but where anything is, difficulties in using the computers to do these things. Any questions? I'm going to stop for a second. Just listen.
Paul, the link that you have sent, do you have your previously recorded videos in it?
Oh, good point. The videos.
I didn't find them.
Yeah, you are correct. And I just thank you for mentioning that. The videos are on a YouTube site that I did not send you the link for. However, and I will. If you are curious before that, you go to youtube.com and look for Newport County Radio Club, and you will find a list of videos that includes a lot more than these seminars. But they're all marked week 1, week 2, week 3 seminars. So I'm sorry I didn't mention that. I'm glad you brought that up, Shania. So I will send you that in my next thing to you, where that link is.
Thank you.
Okay. Okay, if there's no other questions, Brenda, you're gonna have to leave soon, so I wanted to just check with you. You okay?
Yes, I am.
Okay. If you can't find something that you think is available, just email me and I'll send you the link again. Because otherwise I would assume that you do know where the stuff is, or you have access to it. I also sent out the exercise 1, which was the map. The map is not the key, but the techniques within the map are. So I want to get you to do things like that several times so that you get used to it. But please do that map exercise. And if you're struggling with it, let me know and I'll help you through it. Several people have gotten the right answer. In fact, 4 people have gotten the right answer and nobody's gotten the wrong answer. So
But I
it
don't
must
think
be understandable.
he said this is.
Okay.
He wanted us to use the tools.
All right. So I'm going to start with some of this material on these slides here because
It's different.
I'm moving on here. Okay. A lot of the regulations associated with these exams have to do with what frequency bands you will be allowed to use or have privileges on when you get your new license. This tends to be pretty boring stuff, but and there aren't too many tricks to learning it. So you'll have to work on that a bit to try to get the answers to those questions right. What I want to do is show you the reason for some of this is that we are privileged to get access to these radio frequencies. This is a resource that is given to us as licensees to use in a non-commercial way and to hopefully do several things. One is to potentially use that capability in an emergency, but more than that, to advance the state of the art in those areas. And we do that by either using those frequencies and monitoring them, or we use those frequencies to actually, we build equipment that works in those things. We refine it. As a community, we publish a lot of this information and we make it generally available. We do youth outreach and STEM and all kinds of things like that, So this is part of the responsibility of having the license, but it also comes with that privilege to use many frequency allocations that people pay dearly to have otherwise. If we don't use those bands, there's a thing called use it or lose it. The FCC is actually paying attention to how much we use these bands. So if there's nobody on an amateur radio band and they discover this is continuously the case, they could take it away. So don't assume that, you know, life is just don't do anything. We want people to use these bands, or we could lose them. There was a 6. There's also some new bands. There's a 6 gigahertz band that's adjacent to Wi-Fi. That's new. We have the 3 gigahertz band, which could be taken away from us and likely will. This is a little bit older slide, but I just want to show you that these events are dynamic. The bands are not always the same all the time. Sometimes they change. The low frequency bands don't much, and therefore you think that nothing changes, and that's not the case. The FCC does change these rules occasionally. Okay. The FCC, is the Federal Communications Commission, is the United States regulatory body that is the response, the people who issue the exams and give the privileges out as a governmental body. I'm going to go to this website, which I hope you do too at some point. You don't have to do it right now. Let me go back over here.
Charles, this weekend is funny. Yeah, well, tonight and tomorrow certainly. Sunday not bad. The second half of the weekend is looking pretty good for us. You have some rain moving in tonight, guys. If you're stepping out, an umbrella or raincoat, you're going to be walking outside because the rain showers with us.
Okay, I have discovered that the current Federal Communications Commission site is very helpful. In fact, it even explains what amateur radio and satellite services and everything is. What is the amateur radio service? It's all documented here. All you got to do is read it. I don't have to read all this to you. What I'm trying to show you is that the FCC website is actually a good place to visit to find out where these rules on actually come from, what the rules are, and not necessarily to water them down, but this is readable material. It's not something you can't possibly read because it's so technical, nobody would ever know what it was. Here's the thing on operator classes, volunteer examiner things, all those rules that are in the exam questions derive more or less from these pieces of information.
Can you mute the TV?
Oh, is that still working? Robert?
Yep,
Just, I mean, I can mute it if you want, but
please.
let me just look at participants here.
For a credit card machine breach, an employee at the store told police that Foster was.
Yeah, okay. Sorry about that. All right,
Thank you.
okay. Things like, you know, what your responsibilities are, changing addresses, all this stuff is on this website. I'm not trying to provide you a guide to know all this stuff. I'm trying to provide you the link to where it is. And so that's a good reference to go over and look at. Why did I do this one? I'm trying to remember. Let me go over here, find out why I did this. I didn't go back there today. Okay, Part 97 is the amateur radio service law, and it is the actual definition of what your license privileges are and what your responsibilities are. Look at this one, 93.7 definitions. All these crazy words that that are in the test are almost all of them are in here. I mean, what's a control point? What's an earth station? What is the difference? What's broadcasting? It's something you send to the general public. They define all these words that are in the exams in this one page of definition. So if you don't know what a word is, you might try this as a first line reference. Radio quiet zones, not so obvious. What's the amateur civil emergency service? What's a spurious emission? That's probably obvious to all of you. How do we define a space station? Something 50 kilometers above the Earth. You're going to find a lot of the questions come out of simply all of these definitions. Effective radiated power is defined here. So there's a wealth of information just on this one page. I mean, look at them all: pulse, RTTY, SS, all these terms that we're trying to put in context with the questions. They're all here. So it's a good link. That's why I put it in there. Let's see if there's anything else down here that might be. I'm slipping through it. I'm not trying to read you all the stuff. I'm just trying to back. If some of you might be interested in a vanity call sign at some point, if you haven't done one already, you can get any call that hasn't been used and is not contentious. You can get it. I don't think there's much. I think that the definition thing is really what I wanted to focus on. There's a lot of stuff in the regulations about station control. This is the legal definition of what you're supposed to do and not do. The idea is, if you need to know what the legal definition of something is, you can go ask a friendly amateur radio operator next to you, but this is the way to really get the right answer. Okay, so there's a lot of myth in amateur radio. People think they know stuff and they don't. There's cases where people know too much and they explain it all to you, which is sort of what I'm doing. This is where the rubber hits the road here, I guess. Look in here if you're not sure about something, and it's quite readable. I don't think this is as crazy readable. Here's the case on music. Music is a phonics emission. That is, it's a voice signal emitted from your radio, except as specifically provided elsewhere in a section. Communications intended to facilitate a criminal act, encoded for the purpose of obscuring their meaning, and otherwise provided obscene and indecent language, false and deceptive messages, signals, or identification. This is what you're not supposed to do. And as much as I'd like to say it doesn't happen, it does. You're not allowed to transmit music. You're not supposed to encrypt messages or obscure them. But note that the word encryption is not even used in this definition. It's only obscuring. Encryption is not clearly defined as not being allowed, because the overriding concept in this thing is that if you're going to transmit some signal, you have to define or follow the rules as to so that anybody else can receive it. That might be complicated, but you have to publicly identify any special new way you want to use the radio. If you're using what's called single sideband voice, everybody knows what that is who's got a radio license or can know where to look it up. That's allowed, so it's a publicly available thing. The FCC would know how to decode your message if they needed to. Encryption starts to be on the borderline of that. If you encrypt a signal, you may be obscuring it, but there are emergency communication scenarios where that would be allowed. For instance, if you were identifying a patient with respect to something like a HIPAA scenario, and I know we've got some nurses on here too, so you could encrypt, but if you were to encrypt, you would use an algorithm that's publicly disclosed. So you weren't just doing some weirdo thing, you were actually encrypting with a publicly disclosed algorithm. And if the FCC thought that was important, they would contact you and say, what are you doing? And you have a chance to say something about it. I don't think, this is a continuing discussion in the ham radio community, whether encryption is allowed. But I want to point out that if you look at the actual FCC Part 97 rules, the word encryption is not in here, only obscuring things. And by the way, you can obscure things without encryption. For instance, if I tell you that I found this guy fell off his bike on the side of the road, and it's an emergency situation, and I was doing that for a bike race, I may call, bike rider 17, bike rider 13, something like that, which is an obscuring code to get rid of the name. So there's a certain amount of common sense that's required here. It is not a black and white case to use as to where obscurity is. And a lot of times this has not been tested in a court of law. And so if you do something reasonable and public and it's an emergency, it's usually allowed. If it's not an emergency, you should not be transmitting music. You shouldn't transmit music anyway, but if there was incidental music in the background, just because there was an emergency, that's incidental to what you're doing. So I guess I'm pointing out, read the Part 97 rules. If you have a question, that's the real reference. And here's the link. And if it's an emergency, almost anything matters. An emergency, almost anything is okay. An emergency test, if I'm running an exercise, an emergency management exercise, that is not an emergency. So one would want to stay within the rules in an emergency test versus a real emergency. So there's lots and lots of stuff here. And as we talk about various things in the rules, this is the reference to go back to if you need to know something. So I've given you that. Okay. In the United States, the Federal Communications Commission, FCC, is the regulating body. There is an international body called the International Telegraph Union, which I guess I converted this a little bit. One of the questions has to do with what region are we in? So here's a map of the world. All of the Americas and part of Antarctica on these lines are in region 2, and that's region 2. So there you go. You can get this map from this reference. Yeah, done with that one. Okay. All right. As a general class licensee, you're going to have a lot of privileges in the what I call bands that are actually related to low frequencies relative to other things. As your technician, you had the privilege of operating at 50 megahertz or 6 meters and higher frequencies. You probably now know what a band is, because there's like a 2-meter band and a 6-meter band or a 440 band. The band names like 40 are really determined by the wavelength. And this rule shows up a lot in the exam. The actual wavelength is 300 divided by the frequency, or the frequency is 300 divided by the wavelength. So who can tell me what the band for 150 megahertz is? Take 300 and I divide it by 150. And what band is that?
2.
2 meters. Okay. So you know how to use that one. if I tell you, look at the, some of these things are not exact. Like the 20-meter band is from 14 to 14.35. It's not exactly 20 meters. The 75 and 80 meters frequencies are in the same band. So 300 divided by 75 meters is 4 megahertz. 300 divided by 80 is 375. That's not 4 megahertz, it's 3.75 megahertz. So this formula here, if you can remember this, 300 divided by frequency or wavelength, you put your hand over the one you want and then formula is left over. So if I cover wavelength, you divide 300 by megahertz, and if you cover wavelength, that's 300 divided by the frequency. What is the 300 representative of? Anybody know?
Nope.
Nobody? No one? It's the speed of light. Because these are waves and they propagate at some speed. They propagate 300 million meters per second. But since we're talking about frequency in megahertz or millions, you can drop all the zeros and use megahertz for frequency. So 300 divided by 80 meters is what is it? 3.75 megahertz. So this is a handy formula. The number 300 shows up all over the place. So it's a wonderful number to know. Anybody know how far light travel, how long does it take for light to travel 1 foot? Any guesses?
Not very long.
Not very long. That's a good answer. The answer is 1 nanosecond, which is a billionth of a second. So 1 and 9 zeros. So light travels very fast, but that's what this formula is about, the speed of light. Okay, another I will go through the band plans with you at another day. So I have not covered all of the bands and rules and everything with respect to the general class. I'm just trying to make sure you understand what a band is versus and wavelength and frequency. This you should get pretty familiar with. I think you should be able to say, oh, 7 megahertz, what wavelength is that? That's a pretty important thing for you to know for the future, not necessarily the test. Whoops, sorry. Whoops. Okay. Other words that get used a lot are image, phone, AM, CW, RTTY, and data. The FCC regulates not just the use of the band and what frequencies are available. They also identify certain modes that can be used in that band. You can't just do anything you want at any frequency in a band that you have privileges with. You have to restrict your signal so that other people can share the band with you. And in order to make that a good sharing scenario, there are restrictions on what modes you can use. Image is like TV. Phone is the word phone is used to mean voice or sending your voice or sending what is actually sound, not necessarily sound converted to electricity. It does not have to be a voice. It can be just any sound that is restricted to the same frequencies as your voice is. That's important because there are special digital modes that use that very effectively. We're going to talk about all that detail. AM is an old system, amplitude modulation used in your regular AM radio in your car. Some discussion recently as to whether or not they want to delete that from the, a lot of people are complaining about that they might actually take AM radios out of standard cars. And single sideband is a more efficient way of sending voice. It takes half of the room in the band, and so twice as many stations can get on And that's a good thing. So you can share more stations if you use less of the band. And that's why single sideband uses one of the two sidebands. It uses a single one. AM has two sidebands. Single sideband is the transmission of either one. Another mode, I'm trying to use this vernacular so that you see it multiple times. I'm in this introductory thing, I'm going to use words and I'm trying to explain them. When we see them again, we'll go through more technical detail on it. CW is continuous wave, which is exactly what it is not. If I just transmit a single frequency all the time, don't turn it on or off, I can send you no information on that signal. There will be zero information there. The only way I can put information on it is if I do something to it or change its frequency. This is a fundamental thing in radio. CW is actually turning on a single frequency on and off. And that's what we do with Morse code. So in Morse code, if I'm sending dida, I turn my carrier on for one section of time, and then I turn it off, and then I turn it on for a da, which is 3 times as long as a dit. I assume all of you, does anybody doesn't have any idea what Morse code is? I'm guessing no. Nobody needs an explanation of that, or at least not how to run it, just what it is. Okay, so we're turning this thing on and off. And when we do that, we create other frequencies. And we're going to explain that to you technically later. But anyway, that's a mode. RTTY is radio teletype. TTY has been teletype. You don't see many teletype machines anymore, but a lot of people have seen them, especially us old types, where you can transmit what you type. So on a radio teletype machine, you have a keyboard, you type, each letter goes out, it comes back on the other side, it prints it on the screen, on the paper, and that's a teletype. So that's what RTTY is. And data is sort of a catch-all that is anything other than those things. And if you start reading the Part 97 rules, you'll find out that image, phone, AM, CW, CW, and TTY were the basic modes, and they're discussed a lot in the rules because the rules go way, way back. These are not rules that came out last week. These are 100-year-old rules, and they've evolved. So data is the new thing, and there's still definition as to what data is in the FCC's mind, and therefore in your mind, because you have to deal with that. Okay, another thing that will show up all over the place is these crazy unit conversions. We're going to deal with things that have numbers associated with them, like voltage or frequency or wavelength. And these numbers are like all over the place. And so there aren't that many conversions in the exam. Every one of them I have found are not strange. You won't need any calculators to do these things. Surprisingly, you can take a calculator to the test, but you shouldn't. If you need a calculator, it's going to be rare on an exam. Sometimes I used it for confidence building that I had the right answer, but there is no question in the exam pool that actually makes you do anything complicated calculation wise. Almost anything is like almost obvious what the answer should be, as long as you can separate it from all the wrong answers. Okay, you don't have to do complex calculations. So I'm going to give you this as a reference. I'm not asking you to remember it too much, but there's milli, micro, nano, and pico. These are all the small ones. Anything that's a milli something is you take the decimal point of what it is and you move it to the left 3 decimal points. If it's kilo, you move it to the right. So if I had 1 volt and then I wanted to talk about, or I had a watt and I wanted to talk about a kilowatt, I would move the decimal place over 3 and I'd have 1,000. So a kilowatt is 1,000 watts. If I wanted a milliwatt, I would move the decimal place the other way, 3. So I'd have 1 and I go 0.1, 0.01, 0.001, that would be a milliwatt. And so there's some examples here, kilovolts, megahertz. That does not mean you damage yourself, it's just the megahertz. Gigahertz is moving 9 decimal places, and nano's going the other way. So here's the table. These are words that will show up, and there is not a lot of conversion in the exam, but there are a couple places that you'll be asked to know some of this stuff. Okay, other words that are in the exam are secondary users in general exam section 1, section A, question 12. That's what these references mean. So when you go through the question pool, you'll find the term secondary user. Secondary user is someone that's not the licensed control operator of the station. Other things they throw in the exam are things called Q signals. These are short abbreviations for certain ham things. There's one of them that's called, where am I? I'm at my QTH. So my home is my QTH. There aren't many Q signals in the exam, but there are a few. There's obviously a table of Q signals, and you can normally, when you're not taking the exam, you look them up. Or a few of them, you know. I've told you what the FCC means. It's the Federal Communications Commission. We've talked about these terms. Okay, another word is the segments in the bands. The radio bands are split up typically with a voice part and a data part. The voice part is at a higher frequency than the data part. So there's a small data segment at the beginning, say from 7,000 to 7,100, and then a voice segment for which you're allowed to transmit wider signals of more frequencies at once, typically voice. But you're usually restricted to not use more than 3,000 of that set, because that's what one voice band is. Okay, so the reason we restrict this is so we can share better. This is sort of this is a little bit of a review of what I just told you. I don't remember why I put this in here. There's a question on a repeater. Didn't put the reference in. I'll have to look into why I put this in here. 28 megahertz is the 10-meter band. Note that 28 is not the 10-meter band. If I tell you, if I ask you what frequency is exactly 10 meters, who's got the answer? Go back to our formula here.
30?
30 megahertz. That's not even in the 10-meter band. The 10-meter band ends before 30. So be careful. The band is not, the band is a general term for the band is a sort of a general term that's about the wavelength of the frequencies in that band. I just don't want you to be, it's maybe obvious, but it's not, I don't think it is. Okay. I'm gonna move along. Let's see. I just want to double check my stuff here. I got a whole bunch of text here. You don't have to read all of this, but a beacon is a station that transmits so that you can observe if you can listen to it. The problem with a beacon station is that it's always transmitting, so it's not sharing its frequency ever. These things tend to be avoided because you don't. If everybody had a beacon station, there wouldn't be any room left to talk to anybody, right? I mean, all of us put out a beacon station at their own frequency, we'd always be transmitting and nobody would be sharing anything. So there are very specific rules on beacon stations, and that's the reason why there are specific rules, because you should not really typically put out a signal that's continuously transmitting. You should always leave room for listening. This is all the rules about it. There are some questions about it, but I think there's only one or two, so. A beacon can only transmit one-way communications because it doesn't listen ever, right? You see there's some rules on automatically control stuff. You see this little reference over here, 97-203? Where would I find that? Where would I find this information?
Part 97.
97. I just go to the FCC site, look up 97.203, or do a Google search for FCC Part 97.203, and everything you ever wanted to know about the world will be answered for you. Okay, it's 7:30. I'm going to take a 5-minute break for people who want to take a 5-minute break, have a drink of water, and I will probably not really break, but I'm here to try to catch up and answer some questions.
So, I wanted to know if the NOAA station.
Let me catch up to my own self.
So where does it, we did, reactions, raise, yeah, but he didn't get it, so. Paul,
Yeah,
Oh, is the NOAA station? the
I can't hear you.
NOAA Is the NOAA band considered a beacon?
is it what? You're still not,
NOAA.
NOAA, that transmission is going continuously.
the weather station?
The weather station, yeah. Would that be considered a
No, that's
beacon?
not really a beacon. Well, let me try to explain. A weather station is actually a broadcast station.
Okay.
So it's broadcasting one way, like a beacon station would be. Typically, a beacon station is authorized to transmit at low power as well, but it just puts out a continuous signal so that you can see if you can hear it, and its location is defined so that if you can hear it, then you can expect to hear amateur radio stations in that vicinity.
Got it.
So we
Okay.
send out these beacon signals for that reason, more than to pass out lots of information that you would do in a broadcast. But they are similar. As a matter of fact, let me go back here. Must not concurrently transmit on more than one channel in the same amateur service band from the same station. Oh yeah, and the transmitted power from a beacon must not exceed 100 watts.
Oh,
Okay.
okay.
A broadcast station like WBZ AM transmits 50,000 watts. That's obviously not a beacon.
Wow. Wow.
Okay.
No.
There are, I guess what I'm trying to say is beacons tend to be available, but you can't put 1,000 beacons in a channel in a band, otherwise there wouldn't be any room left in the band.
Right. Right.
So they're typically low power things. 100 watts, not that low. A lot of beacon stations now run in very low power modes, like a watt or something, and when you hear them, you know you can hear that area.
Okay.
Does
Thank you.
that answer your question? Yep.
Yes, it did. Thank you.
By the way, there's an interesting point in here too. There's this thing called the National Radio Quiet Zone.
Yes.
Mhm. It's in Virginia, West Virginia.
There's several of them. There's one in
Oh,
Virginia.
yes. I've heard
And
of these.
this has been around a long time.
Yes.
But
Near nuclear.
what they do radio astronomy there and so forth, and so there's very high restrictions on sending. If you're interfering with a national radio quiet zone, you got to get
Right.
off the air, whether you got
Yeah.
privileges or not.
Right.
Okay, but the interesting thing is this has come up very recently, like in the last week on the news, because or in the tech news anyway, because all of the new thousands of satellites that are going into place
Oh, yeah.
are transmitting, and guess what they do? They get picked up by all the radio astronomy stuff.
Uh,
So,
Oh, boy.
so how do you avoid a quiet zone in that case? I mean, these 50,000 satellites flying around, beaming down signals. They don't shut themselves off when they go by a national radio quiet zone.
Of course not.
So, so the whole question of a quiet zone is being raised by the people who run quiet zones. And they're saying, hey, we need to think about how we do this, because if you do it responsibly, we can all live together, and we can listen to outer space and listen to all of these wonderful signals from radio astronomy, and still have networks that let us communicate. So that's actually a current topic. It's an old topic
what is a quiet zone, though?
before the satellites went up, and now it's a new topic. So you'll see stuff like that on the
Thank you.
okay.
What's the purpose of a quiet zone?
So that the receivers that are in the quiet zone will not be interfered by with, and can pick up the slightest, lowest type signals. So if I wanted to pick up a deep space signal
Yeah.
from like the Voyager spacecraft that's several trillion miles away, I would want to put that antenna in a quiet zone. So quiet zones don't transmit, but they listen to very, very tiny signals. Does that answer your question? No? Yes?
Yes, thank you.
Okay. But why do they have this? I don't understand.
Because if they didn't have them, everybody's radios would interfere with the quiet zone antennas.
Yeah, never mind.
You follow that?
Paul, I think now that
I
I'm,
mean, if everybody around a quiet zone had a radio on, they would mess up all this science that's going on.
and I don't think they allow cell phones. in
Nolan,
those
we
areas.
got to figure this out, because every time you talk, you're not talking in a microphone, and I hear Pat perfectly fine, but I can't hear you.
Well, I'm on the edge here. I don't know where the microphone.
Back up. That's what you did. When you backed up, I could hear you.
Okay, when I backed up.
Yeah, like perfect. Like that's perfect.
Oh, okay, thank you.
Okay, so you must be, this is an antenna beam width problem. You must be.
She's in a quiet zone.
Yeah, you're in a quiet zone. There you go. I really want to hear you. All right, let's see. Is everybody back? I don't think anybody's missing. 1, 2, 3, 4. I mean, only Beth Brenda's had to leave. Okay. All right. Now I'm going to take you on a little journey here. Okay. I have a very favorite circuit that I like. It's called a voltage divider. Okay. I will use this circuit over and over and over again. It shows up everywhere in all of the exams. And if you work hard at understanding it, you will gain an insight to so many things. I can't even believe it. I can't tell you how useful this simple little circuit is.
What would I need it for?
Now, the circuit itself may be very familiar to anybody who's done this, but it's got subtle value to it. Basically, all you need is to make the voltage divider is you have to have some voltage, like a battery. I mean, look at this. This physically is what it looks like. Here's a 9-volt battery. It's connected to one of these little color-coded resistors. Has anybody not seen a resistor? You know what a resistor looks like physically? Have you seen one?
Yep.
Let me see. I got millions of them over here. If you need a few thousand of them, I got them. They come like in rolls. I don't know if you can see that, but they come in rolls and like this, and they're in this. Each one is an individual resistor. And if I was putting them in a circuit board, I would be able to put this in a machine, and it would automatically put thousands of these things into a circuit board. So this is a standard component called a resistor. I got one in my hand. Nah. And yeah, I don't know if you can see it. I'll put it near my head. I think you see it better. Close. Yeah. The lighting isn't perfect, but it's got little bands on it with colors. See it? So the colors tell you what the resistance is, but that's not important right now. What I'm telling you is there's a resistor. So let me go back to my slide here. Here's a battery. It has a positive terminal, which is the red wire. And the red wire goes through one component and then another component and comes back. You see that? And schematically, it looks like this picture in the middle here, where I have a source, which is the battery, a wire from the source that goes through some resistance, connects to another one, and then comes back. In this circuit, there's only one loop. It comes from the source, goes around the loop, and comes back to the other side. Think of this as a water pipe if you want. If you go on that WAD1's thing, you can think of this as a pipe, and there's something pumping water around this loop, and there's only one loop. So that's the simplest circuit I can make is one loop like this. But it's really powerful. Okay, does anybody remember Ohm's law from the technician class? No. Well, there's a magic rule that says voltage is current times resistance. That's Ohm's law. I've written it here as V equals I times Z. Don't worry about the algebra. Skip, you can ignore this for now. If I have a current or electricity flowing through this component here, this little resistor, there will be a voltage difference between one terminal and the other. Now, what's the voltage between the black and the red terminals of this battery? You're on mute there, Pat.
9? I don't
9
know.
volts.
From the bat.
This is a battery because it produces a difference of 9 volts between its two terminals. So there's 9 volts at this battery, okay? No matter what you do, there's 9 volts there pretty much, okay? So now we take, and if we connect the terminals of this battery together, which I don't recommend you do, lots of current will flow in this circuit. So to remove the fact that it's a short circuit and just simply ruins the battery, we put some circuit in between, and the simplest one is a resistor, which is this thing which will reduce the amount of flow by some amount. And there's another one here which will also reduce the amount again. So think of this as like a little restriction in the pipe. So I'm pumping some water around this pipe and I get to this resistor, and it's the constriction, and it stops the major flow. And then I go through another one and it stops it a little bit more. And then it finally comes back and it just flows around like that. This is about the most basic electrical circuit that I can show you, but it's also one of the most powerful. So rather than show you 50,000 kinds of circuits, I'm going to focus on this one and keep beating it like a dead horse into you because I'd like you to really understand a couple things about this circuit. First of all, the battery terminals, we said there was 9 volts, right? Can you translate the battery is the same thing here on this diagram. There's a source or a thing that creates voltage. And so between this point here and this point is how many volts? This is the input voltage to this whole circuit. How many
9
volts between here and here? Or across the source? 9.
9.
Because that's the battery, okay?
Got it.
Okay. Now, the physics comes into play here because I don't think it's obvious how much a resistor stops electricity. So the magic rule is to use this thing called Ohm's law, which says that voltage is current times resistance. So if I know that there's a current through this resistor and I multiply that number by this resistor value of 50, I get the voltage. Okay, now in this circuit above here, I actually have a meter in the circuit that's measuring the current flowing through the whole loop. Whoops, sorry. So in this particular case, this meter is reading 90 milliamperes. How much is a milliampere compared to an ampere? Anybody know? Milli.
Kilos, thousand, milli, I don't know, million?
Milli, yeah. It's, well, all right. So if you don't know, you go back to the table I gave you before, which says to move the decimal place
Yeah.
3 to the left. So it's 1, 0.1, 0.01, 0.001. It's 1,000th of an ampere.
Okay,
That's not, and the 90 of them is 90 thousandths of an ampere. Okay. All right. So that's now, all right. So if I have 90 milliamps of current flowing through this guy, how much do you think is running through this guy? The current now.
what is that?
It doesn't matter what the value is. If I have 90 milliamps of current flowing in this resistor, how much current is flowing in this resistor?
90.
90. It's the same circuit. This whatever's going through one is better go through the other one because there's no other place for it to go. And that's the loop. A single loop. Everybody has the same current flowing through them. Think of the water going around a pipe. Right? So there's only one current in this whole circuit, not 1,000 different numbers, just one number, current. Okay. And if I know what that current is, and it's 90 in this particular case, I multiply it by 50 ohms. And if you had a calculator handy, and you were to multiply 0.090, which is 90 milliamps, times 50 ohms, I get 4.5 volts. Okay. So this is 50 ohms and this is 50 ohms. I'm not going to make it hard on you. I'm just going to make two 50 ohm resistors in here. So if I had 90 milliamps flowing through here, I multiply 90 by the resistance of 50 and I get 4.5 volts. Let me do it again. I got 90 milliamps going through this thing. It's also 50 ohms. How much voltage is across that resistor? Same resistor, same current. How much voltage?
Whatever it was the last
4.5.
time.
4.5. So if I add them up, I get 4.5 here and 4.5 there,
9.
9. So
Nine
whatever
watt.
happens here better end up being the same
That's the power source.
as what goes in. Okay. All right. Now here's another interesting thing. What came out was 4.5. No, wait a minute. 9 volts is what went in.
Uh-huh.
I will define what comes out as whatever appears across this output resistor, this guy. This is called the load of the circuit. So the voltage across here, which we now know to be 4.5, we will call the output voltage, V out. So if I put a meter over here, I will measure 4.5 volts, which is the output voltage, and the input voltage is 9. How much did I divide? What did I divide the input by?
2.
2. So this is a voltage divider that divides the input voltage by 2. Not so crazy complicated anymore. Now, the real trick will be to know what you divide by if I just give you 2 arbitrary numbers for these resistors. And this is where it gets a little tricky. But I've already showed you one thing. If I make the 2 equal, how much comes out from the input? We put in 9, what do we get out?
9.
We put in 9, what did we get out?
Half that.
What was the voltage across this output resistor here? Or
Oh,
load?
output of 4.5.
4.5. So I take the input and I divide it by some number to get the output. And what's that number?
2.
2. Yeah. Okay, now take a look at this formula here. I've got the load. I've got the load plus the source. Okay, this was 50, this guy, and this was 50. So what's this say? This is 50 divided by 50 plus 50, which is what? 50 plus
2.
50.
2.
50 plus 50.
100.
100. And the top is 50. So I got 50 divided by 100. What is that? What is that?
2.
50%.
Half.
Half.
So 1/2 is dividing by 2. Multiplying by 1/2 is dividing by 2, right?
Yep.
So I take my input voltage, 9, and I multiply it by this factor, and I get my output,
4.5.
4.5. Now let's do another example where it's going to get a little trickier. I'm going to make this one 50. I'll leave that one at 50. In fact, I'm going to leave that at 50 all the time. And I'm going to change this to 100. The load is 100, the top. And the sum is 100 plus 50. So what's the bottom? 100 plus 50.
150.
And the top is 100.
100.
So it's 100 divided by 150.
2/3.
2/3. So whatever voltage I have here, I multiply by 2/3. Anybody know what 2/3 of 9 is?
6.
6.
Yeah.
Yep. Yeah, 6. So I would measure 6 volts over here. Okay. This whole thing about taking the output device, dividing it by the sum of the 2 things in the loop, that's the magic formula for a voltage divider. Now, this concept, we will later convert to all kinds of things like antennas, loads, 50 ohm transmitters, filters, all kinds of circuits. But this very simple principle that if I define this to be the output and it has a value of X, I can divide, and this is a value of Y, I can take X divided by X plus Y, or load divided by load plus source, multiply it by the input, and I get the output. So I now ask you to take a look at the same circuit. Instead of being 50 ohms over here, always keep this one at 50 because it's easy to remember. And we'll change this one. This used to be 100. Let's make it 25. Maybe that's not a good example. It's okay. We could do that. It's the output's 25, and we divide it by the sum. How much is the sum?
75.
I'm sorry, 50, yeah, 50.
50 and
25 divided by 50 plus 25,
75.
75. So it's 25 divided by 75.
1.
That's
No.
a quarter. No, it's a third.
A third.
Oh.
So now we had 9 volts and we multiply it by 1/3. And what do we got?
3. I mean,
Three.
yep,
All right. So we did 3 things. We put a 50 ohm resistor on the output and we got half of the voltage. We put 100 ohms resistor on the output and we got 6 volts. And then we put 25 ohms resistance on the output and we got 3 volts. So we can put any resistor we want on the output and get any voltage we want out. Isn't that handy? So if I
Yes,
had a battery of 9 volts and I wanted to create 4 volts or 5 volts or 6 volts or 2 volts or 1 volt, all I got to do is adjust this one value of resistance and I can get any voltage I want by this formula.
why do you want to do that?
So I'm always getting something smaller out. So I'm dividing my original voltage by some factor to produce this output. And that concept is very broad across all of the technologies we're going to be talking about in radio. So I'm going to leave you with an example. I didn't think of one, but instead of 50, always use 50 for the source. That's this guy. That's called the source resistance. And change the, maybe I'll give you a different answer. Maybe I'll ask you for, I've got 9, oh yeah, okay. Suppose I had a 10 volt battery
Yeah,
and I wanted to get 6 volts.
so you want to take 3 volts away from
4.
Yeah, that's it. By the way, that's an excellent point, Pat, taking 3 volts away,
4.
or 4 volts away.
4 volts away, yeah.
Yeah,
So the 4 volts that goes away is going to go across the 50 ohms and the 6 volts is going to be on the output. I don't even know the answer to this. I'm asking you to do something here. I didn't, let me do the algebra in my head here. While you're doing that, let's say I get 10 volts in, I multiply it by I divided by R plus 50. I want 6.
what's that, baby?
So
Okay, your bloody data.
0.6 times R plus 50. 0.4. I'm doing it the hard way.
Yeah.
I'm just to get the answer so we can go back and do it. Well, the answer is 125 ohms, I think. So let's go back and put the answer back in. 125 divided by 50 plus 125. That's 125 divided by
170.
175, right?
Yeah. Okay, so use my calculator. Let's see.
No, that's not the answer. Oops.
It isn't, not at all.
No,
That's coming out to 7 volts. 7.1 volts.
Where's my?
Yes,
So I did that wrong, but 125 will give you 7 volts, but we wanted what we want. We wanted 6 volts.
6.
What did I do wrong? 10 times the output resistor times the sum of the output resistor and 50 is going to be equal to 6.
You silly guy.
So I divide that and I got R over R plus 50. By the way, there's none of this algebra on the test. 0.6 R equals. Oh, I know what I did wrong.
Is it 75?
With 75? All right, let's try it. 75 divided by 50 plus 75. That's 75 divided by 125.
Yeah,
Oops.
it's 3/5.
6.
Six out of 10.
That's 0.6, right? So
Yep.
10 volts times 0.6, 6
Yep.
volts. So we get a 75 ohm resistor. We put it in series, it's called, with the 50 ohm resistor, and we get 6 volts out. Okay? So the rule here is you take the load and you divide it by the load plus what's called the source resistance in this case, and you get the output by multiplying the input by that magic number.
Let's walk this thing through again.
Sure, yeah, go ahead.
Because we got the 10 volt as the source.
Yeah,
And then we said we have to have a 50 ohm resistor right away.
yeah, I'm gonna pick that because I don't want to change it, just because that's very common.
Okay, so then that's 50. And then you're saying the next one is gonna be what?
The next one is the thing that we're trying to find. We're trying to find what resistor value we need to put in so that it,
But think about it, what the 50 ohm resistor has already done to the voltage.
you can think of it that way if you want.
What's it done?
The 50 ohm is removing the 4 volts that Pat wanted to get rid of.
No, it's reducing it by 5 volts, right?
No, if there's 6 volts out and 10 volts total, there's 4 volts on the 50 ohm resistor.
No, the 50 ohm was the first resistor
Right,
in the sequence.
right.
What comes out of that?
Well, the output side of, one side of it is 10 volts. The other side should be 6 volts because that's the output that we wanted.
No, but I'm saying after the first resistor,
Yeah,
what's the output going into the second one?
6 volts. Because that is the output. The top of the load resistor is the output. That's what we're trying to get. We're trying to get 6 volts, right?
No. If you have,
Look at my
Yes.
diagram again. See this point right here? And it's right between the 2 resistors?
yeah,
That's the output.
okay,
Whatever the
the output,
voltage is there,
the output of that first resistor is what?
right? Yeah,
How many volts?
6.
Why? Because you had 10 going in and you had 50%.
No. In this drawing, I have 50, but if you put the 120, we got the answer from Shadadi. He said we want 75 ohms. So this is 50 and this one's 75.
I don't get it.
Okay, that's all right. That's okay. Start again.
No, it isn't. Okay, I gotta understand.
No. I mean, it's
I
okay
don't
that you
understand
understand now.
either.
I want you,
Does everybody else understand it?
no? Okay, all right.
Not really.
I'm gonna beat this circuit.
Exactly.
I'm gonna beat this circuit to death because the more intuition you have on this circuit, the better all the radio stuff's gonna make sense.
Okay, you go in with 10 volts, right?
Going to 10 volts, yeah,
And if you look at your diagram and the first resistor is on this diagram is 50 ohms, right?
yep,
And we're gonna use that same resistance.
yeah. I'm just gonna define the problem to always use 50 ohms at the source.
Okay, so that we come through the source and after 50 ohms, what do we have for voltage
Well,
going into the second one?
the solution that worked was 75 ohms.
No,
I can explain if
Yeah,
If
go
you
ahead,
let
go
me.
ahead, go ahead. I want somebody else to talk it out. Go ahead.
And is it possible the two kind of share screen and write it?
You want me to, you want to share your screen?
Yeah, and
Okay, hold on
write
a
it.
second. Yeah, hold on a second. I have to fix that. Hold on. Okay, I'm gonna stop my share. If you want to put your screen on, go ahead. We're fortunate to have Shadadi with us, who's a biochemist in state of Arizona. So
Yeah, give me like,
we're not gonna confuse them with arithmetic, but that's all right.
give me like a minute.
What did it say?
All right. So the problem is if I get 10 volts in, I got 50 ohms on the source, 75 ohms on the load, I get 6 volts out. That's the answer. The question is, do you understand where we got it from? And that's what I'm trying to keep going with you.
Can you see my shared screen
We
now?
can, yeah, we can.
So I'll write here and see if I can explain it to you guys. So we have, so I'll quickly draw the circuit here. So we have the, suppose we have the battery, which is 10, so
10 volts.
10 volts. My hand is shaking.
It's okay.
And you have one resistor. You consider it as R1, which is the source. It is 50 ohms. This is the sign of ohms, by the way.
Yep.
And then you have.
It's a Greek letter, so we're trying not to bring up Greek letters all the time.
Oh, yeah.
That's okay.
Yeah, then you have R2, which is the load here, and which we want to find. So consider this as X here. So we have to find this X. And this is what I found to be 75 later, but I will show you how. And then
Now that line that you just drew is the ground reference. That is called 0 volts.
I see.
So that's the point where you measure everything from. So go ahead, continue. I just wanted to make a note that you just drew the ground line. That's all.
So we are gonna measure the voltage between this point and this point, which is the voltage between R2. And so our total voltage here is 10 volts, and that is gonna get distributed between the R1 and R2. And the formula that we had was total resistance is R total times multiplied by the current. The current was, can you remind me what was the current?
Actually, they do the current in this case. So the current is 10 volts divided by the sum 50 plus 75. So
I'm lost.
I actually found it in a different way.
you don't really need the current, but you don't really need the current.
You don't need the current. So from 10 volt, I am multiplying with the resistance with certain value y, suppose say y, where we are finding going to 6 volts. So we are trying to reduce it to 6 volts.
Right.
Y equals 6. Oh, I can think I can understand.
So that y equals 6 by 10 volts, which is 0.6 volts.
Okay, now y equals 6 volts over 10. Voltage equals
And
0.6. Now, I got it, but I did it 3/5. Like I did it with a fraction instead of a decimal. Okay, I think I'm getting it. Well, the decimal for 3/5 would be 60. Would be 6 over 10 is 6. Would be
And
6 over 10. Okay.
Hey, Terry,
If I multiply
how
each-
familiar are you with this topic?
Yeah, not so much.
Okay, that's good. All right. it sounds like a simple circuit, and it is from a circuit standpoint, but reality is it's not so simple. But if you understand it, you will understand all kinds of stuff, and I just want to beat it up.
Okay.
Because and if you don't get it this time, we'll be doing it again. So you'll have another opportunity to see it again and again. But I do want to show you a tool. Siddharthi, can I hold?
Yeah.
Could you just hold your thought for a minute?
Oh yeah, yeah.
Yeah. Let me unshare your screen for a second. I want to show you guys a tool before it gets too late. Okay, so I'm going to introduce you to a crazy program that I found that I really like. So let me close this and this, and let's see. Again, nobody's sharing right now, right? So give me a second. Let me get this back. I'm not in my, oh, there we go. Share screen, share screen. Okay, I'm gonna create a new web page, and I'm gonna go to a website called tinkercad.com. Oops. All right. Take a note. And this is free to use. And what you will be asked, if you want to use this, you will have to sign up. So you just need an email to sign up. You can be a student, just say join a class or whatever, or you can create your own personal account. Sometime next week, I suggest you try this tool out with an email address. You create that. I've done this before, so I'm going to sign in. You can sign in with your Google account if you want. Oops, sorry. If you have a Google account, you can do that. I forgot which one I used now. I did this so many times now. Sometimes I can also send you a. All right, so Tinkercad. I'm logged in now. So when I got my account, Tinkercad will do several things. The one that I want you to look at is a thing called circuits. See this over here? You can draw three-dimensional things if you want. That's not what I want you to do. But I do want you to take an experiment where you can use Tinkercad circuits. So I'm going to, so there's this little button that says tinker this. So I'm going to do that. And I'm going to get a magic screen. Okay. Now, I don't want that, so I'm going to get rid of it by deleting it. Okay. When you start, this is the blank screen you get. There's a workspace over here and all these wonderful electronic things over here that we can now build a circuit. So we can take a battery and we can put it on our workspace and we can rotate it around. So we had a battery. What do we need now? A resistor, right? So we'll take a resistor and we'll put that over there. Only what resistance do we want on that? 50 ohms?
50.
So I want 50, and I don't want K ohms, I want ohms. I have to select ohms, okay? Note that the color code changed to be the color code for 50. I'm not asking you to learn the color code, I'm just showing you that the program automatically puts the color code on a resistor for you. Isn't that cute? So here's our 50 ohm thing. Now we need one more resistor, right? And where do we want that to be? 125 ohms?
Pick one. I have no idea what you're doing.
Well, oh, it's not 75 ohms. I'm building the circuit that we just designed.
For that, we will need 10 volts of battery then.
Yeah, all right, and we need a 10-volt battery. Okay, I can do that. Wait a minute. Can I do that? Oh, that's interesting. I can't make a 10-volt battery. I forgot that. Well, rather than, I think I better change to a 9-volt battery for now, but I can show you how to make 10 volts in a minute, but I don't want to confuse you with that information. All right, so what did I do? I took the positive terminal and I wired it to this resistor. And I connected this resistor to that resistor, right? And I connected that guy to this guy. And I've now made my little voltage divider circuit. Okay. Don't worry about prettying it up, but you can do this like this if you like to make it nice and square. That's not important, but I like it to look right. And I can color this wire red if I want by just changing the color at the top. Sorry, the color at the top to red. And I can make this black. I'm just showing you things you can do with this program. Okay, so now I've made my little voltage divider, but I need to measure the voltage, right? So I need a meter that I would go in my bench to find. So I'm going to grab my little meter and I'm going to put it over here. And I want to measure voltage, so it's set up the voltage. I can measure current and resistance, but I want to measure voltage. And now I need to hook the positive terminal to where I want to measure the voltage. Oops, sorry, didn't cap. You got to wait till you get it in the little red square here. And then you have to hook this to ground, which is the other side. Saying, hey, that's ugly. Okay, so what I want to do is I'm going to rotate this around. And that's not good. Turn around again. Sorry. Guess I'm going to have to leave it like that for now. Okay, I'm going to make this one red just so that you can see the difference. Okay, and now I've drawn the circuit. I've actually wired it just the way I said. Can you see this button over here that says start simulation? I push that button and it's giving me 5.3 volts. Now that's not 6 because this is 9, but if I made this 10 volts, that would be 6. So you can make these circuits on your own for free and test the value that you get here. So what was the one we did with 9 volts? We took 50 ohms and we did, let's go back to one we did before. Let's say we want to make this 50 ohms. Let me stop the simulation. Go to this guy and we'll make him 50 ohms.
Oh, this is all well and good, but I don't understand the formula. I mean, it's pretty and all it's fun and moving components.
No, what? Yeah, I understand.
But if you don't get the Z load over the Z source, and the concept, all this is decoration.
I agree. So what I'm trying to say is, once you've actually determined what you think will work by the formulas, you can build it and test it. Is what I'm trying to say.
That's fine.
Okay, so
That's fine.
okay, so now just for kicks, let me it's like, I got one other quick thing I wanted. I'm going to do one more quick thing here, see if I can. I want to introduce you to the tool. I'm not trying to make you an expert on the tool. I just want to show you that these tools exist now So instead of us getting together in a place and me bringing a whole box of resistors and some batteries and some meters, we can do these experiments in the class without without necessarily getting together and buying components and sticking our fingers with the ends of the components and making them bleed and stuff. So this is a tool that I wanted to introduce you to. What? Let me look for power supply. There's this magic. There's a magic device here called a power supply, which I can set to 10 volts if I want. This is actually a programmable battery. And what I'm going to do is I'm going to eliminate the, bear with me a second. I'm going to connect positive terminal of the battery to here. And the negative terminal of this to here. And I'm going to set start. And now here's our 10 volts. Here's half of it because I got 50 ohms and 50 ohms. I'll stop that. Change this to, what did we say, 75? And I start that and we get 6 volts. So there's a real live example of the same thing we've been talking about. This is what I'm trying to show you. Okay, I mean, not as pretty as the other circuit because I didn't clean it up very well, but you don't have to clean it up to make it work. You just have to clean it up to make it understandable. I should have made this one. Oops, I didn't stop. You got to stop to change it. So you got to make, we should make that one red, for instance. And do something like this and move it around so that it's not in our way. Make it nice and square or something like that. And we start that. We get the same answer, of course. But I mean, I gave you this formula and I, out of the blue, and I didn't, what's the practical value of this? Well, the practical value of this is that this voltage divider thingy is used everywhere in radio. And the specifics of the radio system is this battery thing is your radio. It includes this 50 ohm resistor when you bought your radio. So your radio plus this resistor is really the radio. And this point is the connector at the back of the radio. And this is the antenna. This thing over here. So if I have a radio, which is this thing, and an antenna, that's a voltage divider. And so we're going to be able to use voltage dividers to deal with much more complex situations than just a couple resistors. But this is the basis. It always comes out that the load divided by the sum or the total times the input produces the output. And that's what I'm trying to say. Now, I don't think you've all got it, but I've showed you a new tool that's free to use if you want to play around with circuits. This tool is much more elaborate than I'm showing it to be. But it's a great toy and saves you from buying a lot of crap that you will then throw away. So I entreat you to try it out, even in the simplest case. And if you have an example, you can save it and you can actually send it to me and I'll show you what's wrong with it if it's not working right. Okay, so that's that. All right. The last 2 slides. Okay.
A lot of background noise.
Background noise. Hold on.
I got a job lot. They got a protractor and a compass set. $3 I want to get.
Yep, job lot's the place to go.
When I do circuits.
Okay. All right, the one last thing, the one thing that I want to show you how to do, and I'm trying to get my stuff out of the way here. Why, I want the slide before that. Okay, here's an example of what's called a unit circle. Basically, you can, let's see, what I'm trying to have you do is draw this six-sided hexagon inside of it. So you can take your circle compass to make a circle. And let's see, all the red lines, all the lines on this red are all the same length. These red lines are the same length as from A to B. So if you put your circle compass here, draw a circle, then move the A point to one of these points, like here, and then go up and touch the circle. That's the same distance. This distance and this distance are all the same. You can find these points and make a nice hexagon. I don't have time to really manually do this for you, but this would be a good exercise of practicing with your compass and making a shape. And for those of you who know all about circles and circumferences and diameters and pi and all of that, this is going to be pretty boring. But there's a few interesting things here. How far is it to go all the way around? Well, let's say this is 1 from A to B, right? That the distance is 1. Make it anything you want, miles, inches, whatever. Start over here and go along here. That's 1. Then another 1, and another 1, and another 1, and another 1. How many ones did we do?
6.
6. So if I were to follow the path all around here, the real circle, would I expect that number to be more than 6?
Oh,
What do you think?
always going to be 6.
If I follow the red lines, but if I follow the black line, you think it would be more than 6?
Yes.
Yes,
Yes, it would.
Yeah, it would be more than 6, right?
If you use the radius, it will only be 6.
I'm not sure you're following what I'm saying, Mike. If I start someplace and I follow the red lines, I will walk 6 miles, right? We all agree with that? Anybody disagree? No. Okay, now instead of walking along the red lines, I'm going to walk along the black line.
Well, then you're going around the circumference. That's different.
Right. So will it be more than 6 or less than 6? That's all I'm asking.
More than 6.
Yeah. So we know that the circumference of the circle is something bigger than 6. Anybody know what it actually is?
Be pi d, so it'll be pi times 12.
Pi times 12? That's 26.
Yeah, because it's a diameter, not the radius.
But the radius is 1.
Oh, sorry. Then it's 2. 2 times pi.
Right. And that's the amount of distance it takes to go around the unit circle. 2 times pi.
2 pi's.
That's a magic number for a unit circle. The unit circle is believe it is also like the voltage divider. It's a fundamental drawing that we're going to use for all the modulation schemes on a radio. So the way all the way around is 2 pi, and there's a visual perspective of what it is. Now, let me show you one more thing. Let's suppose we're running around this magic circle like it's a racetrack. Here's a two people running in a race, running around this racetrack. And let's look at some of the text here. If I run around the circle once every second, that's called a frequency of 1 hertz. We've all been talking frequencies, 2 million hertz, 5 million hertz, 2 billion hertz. If I run around this circle once a second, that's 1 hertz. If I go it faster, if I go around 2 times this, if I go, sorry,
2 times a second.
2 times a second, I will be at 2 hertz. So this going around in a circle is equivalent to some frequency on our radios. Now, I want to describe a thing called sampling. If we were to go around the circle and only mark down a little mark wherever we hit one of these intersections of the hexagon, we would have a location little circle over here maybe, and a location circle here, and a location circle there, and here and here. We wouldn't know what happened in between. We would only know that we were here at one time and we were here at another time, but we would not really know where we were in between. In a radio, if I do that and I measure this point, and then I wait a little bit of time and I measure it again, that's a word called sampling. I'm sampling my voyage around this loop. And so if I decide that I'm going to sample every certain number of seconds, I will just mark my location along here, but I would not know where I was in between. Okay. Samples are a word that I want to talk about more in another talk. Okay, so let's see what happens when we have 2 people running around this circle. Okay, so I was running around once a second, but I had a friend that ran a little faster, which at 1.5 hertz. That's only 2/3 of a second to go all the way around. Don't worry about that math. If that's the case, when you make it to 60 degrees over here, you go over here and you go over to 60 degrees, your friend will have he's going faster, so he'll have gotten to 90 degrees, which is this point in between here. And when you are at 120 degrees, he's going to be at 180 degrees. You can verify this if you want. But what's going to happen is the 2 of you are just going to separate, right? You're going to, as you run around this track, one of the faster person or the guy going around the guy or girl, I put the girl ahead, by the way, in this picture, just to be friendly to everybody, because they're usually ahead anyway. But anyway, what I want you to think about is that when 2 people are going around this circle, their positions are separating if they're at different frequencies. Okay, and so the difference between those 2 things will change what their angle is and what their separation angle is. There's 2 different things going on. One is where you are around the circle, you know, like I'm here, then I'm here, then I'm here, then I'm here. And then there's the other person where they are. And then there's the difference between the 2 of you. And that is the difference between those 2 frequency numbers. And you will separate by that difference. And then eventually you'll actually catch up to each other. And then you won't know where the first one, who was ahead or who was behind. Because if you're both going around and you're separating, and then this one catches up, you can't tell who's ahead or behind anymore, right? Until you separate. Okay, that effect shows up in all these radio things. Okay, And the amount that you move along the circle, we give it a name. We call it phase. So if we start off at 0 phase, say we call this 0, and we move to here, we made a change of phase of 60 degrees. And we never talked about frequency at all, right? I mean, we did before, but I'm saying, if I can describe what's going on, if I tell you how much phase or how much angle I change in a certain amount of time. So if I change 60 degrees every second, then I know that I'm at 120 degrees in 2 seconds and so forth. So the rate at which I change phase is a key element to this description. I'm telling you this because I think everybody likes to talk in terms of frequencies. They shouldn't really do that. They should talk in terms of phase, because the frequency takes, you have to go all the way around to get frequency. You have no idea what's going on in between. If I tell you I'm going around at 1 hertz, you know every 1 second I'm going back to the same place, but you don't know where I am at any one point in time. If I keep track of phase, I can keep track of where I am along that circle. And so when I have 2 electrical signals, and one's at one frequency and one's at another, what I really want to know is how much their phase is separating, just like the 2 runners. So if I know the phase rate of one and the phase rate of another, I can just subtract them, and I can predict where everybody is with time. This is what modulators do in a radio. You ever heard of a modulator? That's what it does. So next week, when we get into things like impedances and so forth, you're going to see that an impedance is nothing more than one of these, than a position on this circle. Okay. Now I'm going to show you one more thing. I'm going to go back to my where am I? On my slides, and I'm going to give you one more reference drawing. Oops, it's over here. Oh, by the way, never mind. This is the answer to the map exercise. The distance after the first 2 jaunts was 7.8 miles. And Shahadi pointed out that you also end up at 148 degrees. What you solved here was a little right triangle, by the way, where the one side was 5 miles and the other side was 6, because you turn 90 degrees over here. And the answer was the square root of 5 squared plus 6 squared, for those of you who remember Pythagorean theorem. So the length of that, for you to get from Newport Airport to Fall River, was 7.18 miles. Anyway, that's lovely. Let me go to slide 30 over here for a second. And this is a chart that you won't memorize on the first pass, but I want you to see it. Whoops, come on, Paul. Okay, this is a chart that I put together that has all of the magic words that are in the exam, and there's a lot of them. One of them is called resistance. That's just a number along this axis. See, it says resistance. There's another word called impedance, which is actually one of those arrows that we draw on a map. It's a vector. Impedance needs 2 things. It needs this direction and it needs this direction. So if I want to know what this direction is, I look over here and it tells me X is the reactance. X can be positive, it can be negative, but resistance will always be positive. That's another subtle point, but all of the words for the exam are in here. So make yourself a picture of this, make yourself a printout of this page. And I've defined the symbols: Z, impedance, R for resistance, X for reactance, G for conductance, B for susceptance. These words show up in the exam all over the place. They're all on this page. So take a copy of this page with you during the week, look at it, look at the words, and don't worry about the formulas or any of this stuff, but you almost have to understand this drawing in order to know what all these terms are, but they're all there. And they're very easy to confuse because reactance and resistance both start with R. There's inversions. There's one divided by all of these things, which are the other ones, but they're all on the same drawing here. So carry this around as a reference and use it for the next 6 weeks. And after the end of 6 weeks, you'll know all these terms just like that. Boom, 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 boom. And you'll be passing the exam like that. I don't expect anybody to remember this on the first pass. Please don't think that I'm trying to say that. But just take a copy of it and take it with you. Keep looking at it. And let's see. Let me go back to my last slide. And let me see. That was the map thing. So Z is a vector. And how many numbers does it take to describe a vector?
2.
Ooh, I'm never going to ask you to do 3. I'm only going to
At
ask
least
you to
2.
do 2, but I'm going to ask you to do more than 1. Because when you were a technician, you only did resistance and voltage. That's one thing. That's a 1 number description of something. If you can handle 2 numbers, you're all set to do alternating circuits. And that's what the point I'm trying to make for you. I'm going to leave you with one encouraging note, which is slide 53. No, 50. Oops, my slide numbers changed. Uh-oh. Something changed. Oh, here it is. Well, 57. Oh, I put the wrong numbers. Okay. Anyway, last point. There's a thing called decibels. Pretty interesting mathematical subject. If you're doing a general, forget all of the math. Don't do any of the math. All right. There's 2 questions on decibels on the general, G5B1 and G5B10. Okay. The question 51 says, how many decibels is half? And the answer is 3. dB rhymes with 3. So that's a way to check what the right answer is. And then there's another one that's this question, G5B10 says, what's the power loss for 1 decibel? Well, I can do that for you. I can do all this math and says that 1 dB means about 80% is transmitted. So the loss is 20.16%. And that's lovely, but you're never going to remember that you're never going to remember that during the test. You do not need to do this calculation. Memorize simply that a 3 dB change in power is half, and that the magic answer to this question is 20.6. And then you'll have all the decibel stuff covered for the exam. You won't have to study decibels anymore. Fair enough? Okay, those are little hints that I'll try to tell you. Decibels they're not that complicated, but they are complicated. So I'll go over this again later, but all you need to know for the general are these 2 things, 3 and 20.6. Fair enough? So I'm going to leave you with that for the week, and I'm going to ask if there's any questions. That's the end of the slides for tonight.
Paul?
Okay, this is the process. I'm going to try to study. We're going to look at procedures and laws, special things you got to memorize, like bands and where the bands are and what they mean, why they're that way. And then the other half, I'm going to do simple things that may not really be that simple, but we're gonna do examples of circuits and things, and I'll translate that knowledge to modulation, uh, loads, antennas, matching, Smith charts, all kinds of stuff. But that's an adventure. That's not for this week. Any questions?
Paul, I have that algebra part written.
Oh, yeah, you want to do that again?
I can quickly go over it. It's already written now.
Yeah, okay,
So
anybody that, yeah, okay, let me stop sharing. You should be able to share now.
thank you. Okay, can you all see
Yep,
it now?
you see it. I see it.
So what we were trying to calculate. Oh, sorry.
You moved
Oops.
something.
Yeah,
Oh,
I clicked
okay.
the stop share accidentally.
Okay,
So what we are trying to calculate is the ratio of the resistance or the load and the source resistance that we have to multiply with the input voltage to get the output voltage across the resistance 2. So the 0.6 volts, or actually the 0.6 value, it's just a ratio. It doesn't have units. That you are getting is actually the ratio of the resistances. So this is the ratio of resistance, and I told that we can consider the load resistance as X, and the source resistance we are considering it to be 50 ohms. So load resistance over source resistance plus load resistance equals Y, the value we calculated, which is 0.6 ohms. So from here, you just calculate the value of X, you'll find it to be 75 ohms. And the same way, whenever you have a different value of voltage, if it's 9 volts, and you want a certain other value, like 5.36 volts, you can write it here and then calculate X from here.
so this is how to do it for an arbitrary thing. None of this formula is on the test per se. You'll not have to do a computation like this for the test.
Yeah, this is,
But the principles behind the things on the test relate to this voltage divider thingy. And I think if I just give you the resistors, you should be able to get the voltage out. I think that's what I'd like you to know how to do. If I give you the 2 resistors, can you come out with the output voltage if I give you the input? This is the nice algebraic way of finding out what resistor you need. But no, there's no problem like that on the test. There's a, that's what I'm gonna say, I guess. I'm beating a dead horse there maybe. But in fact, in most of everything I've done, I've tried to avoid all the algebra involved here. But if you know it, it's really handy to know. It's fine.
yeah, if any one of you have questions, you can ask me, or yeah, you can ask Paul.
Oh, that's nice. Thank you.
And I can probably share this or send a PDF of this. I'll write it nicely and then send it.
Yeah,
That would be great. Maybe I'll understand it then, because I don't understand.
that's all right. I'm trying to tell you again that I'm not expecting you to know voltage dividers inside out as a result of this talk. What I am telling you is the better you understand voltage dividers, the easier it is to understand all this other stuff. And so I think you ought to just think about these voltage dividers. What did that mean? Input, output, load, resource, voltage in, voltage out. That picture is everywhere in all this theory of radios. Okay. Any other questions? I got 10 minutes if you need anything else. Want to do another problem?
I like to say,
I know you're just dying to calculate more voltage divisions. Like, like how do I get 1 volt out of a 10 volt battery? Or how do I get 5 volts out of a 9 volt battery or something like that? Those are fun exercises. And if you want to try it out, use Tinkercad, give it a shot, try to get an account going, and then you can do all kinds of magic circuit things on your own for free without burning your hands on soldering irons or sticking little component things into your fingers. This is the big problem I have when I teach little kids circuits, that they they tend to be, they tend to start putting these things together and then you end up with Band-Aids all over their hands because they're sticking components in themselves. So it's safer. Okay? See you next Friday.
All right,
Any questions on timing, or if you have if you can't find something or you want to, just let me know. I owe you the YouTube link, but you can find it on YouTube by looking at Newport County Radio Club, and you'll find the seminars that I had recorded in the past. Oh, let me stop recording. So I don't. And I will try to post this as well. I mean, it's a repetition of a lot of stuff I said before, but